And good afternoon if you're joining remotely or from any other part of the world. Welcome to the first round of technical sessions at the Water Security and Climate Change. And we are now meeting for the technical session called Informing Decision Making for Water-Related Risks. We will be having 5 presentations in this session that come from different parts of the world. We cover 3 continents, Europe, Asia, and Latin America. And we have speakers here from India, Turkey, Thailand, Germany, and well, I think we have 2 affiliations from Germany, but one of the speakers is in fact from India. And as the session title already tells us, we will be looking at water-related risks like floods and droughts, water extremes, which I think are all covered by the upcoming presentations. And the question of what scientists need to do in order to assess them, but also to lead to a more informed decision-making. I would now like to introduce the first speaker, Mr. Sabyasachi Swine, who is from IIT Roorkee in India and who will be giving the first presentation here looking at the impacts of climate and socio-economic changes on drought vulnerability. The floor is yours.
Hello. So a very good morning to one and all. Myself Sabyasachi Swine from Indian Institute of Technology Roorkee, and I'm going to present on this assessing the impacts of climatic and socio-economic changes on drought vulnerability over a transboundary river basin. So this is a multi-dimensional perspective. So droughts, as we all know, among all the natural disasters, as per the World Meteorological Organization, have the most frequency and duration, and also they affect the large areas as well as population. Basically, droughts can be defined as the abnormal deficit of water persisting for a longer duration. But the exact definition of droughts has always been a very challenging scientific endeavor because of several factors like spatio-temporal variation in water demands and association with numerous hydrometeorological variables. For example, there are different types of droughts. When we define droughts, basically from the conceptual point of view, they are defined into meteorological, hydrological, agricultural, and socio-economic droughts, so as we all know. And the assessments are based on indices which are specific to these drought types. So these are the typical propagation of drought from one form to another, that is from meteorological to agricultural to hydrological, and then the socio-economic droughts. So this is further aggravated by the water scarcity and the land degradation and increase in population, leading to lesser per capita water availability for the drying of wells and problems of water conservation. And also several studies have already projected that India will face a very large number of droughts in near future, and particularly there will be the impacts of anthropogenic activities on the global droughts, frequency, duration, and severity will be further aggravated. So these are some of the reports, and despite of these pervasiveness and repercussions associated with the droughts, so editorial from Nature in 2019 says that there will be very severe impacts in future, that is up to 700 million people will be compelled to leave their homes because of this drought impact. Still, the drought is relatively under-researched. Coming to the motivation and objective of this study, so as we know that the characterization of the droughts are mostly specific to these sector-specific drought types, say meteorological, agricultural, or hydrological, we generally fail to incorporate the impacts of this groundwater and the socioeconomic or anthropogenic issues. Say groundwater is the major source of water supply during drought periods, but most of the indices which are assessing the hydrological droughts often ignore it, and also the socioeconomic factors that control the aftermaths of droughts. For example, the land use, land covers, or the population density. These things are generally ignored. So the objective of this study is to circumvent this issue by proposing a multi-dimensional framework for comprehensive assessment of drought vulnerability, which will include all the different aspects, say hydroclimatic, socioeconomic, and physiographic information. So this is the study area, that is Narmada River Basin, which is one of the largest river basins of India and the largest west-flowing river, having an area nearly 99,000 square kilometers. It is located in the core of Indian monsoon region, and it's a transbound river basin which covers 4 riparian states. These 4 are very large states of India. So it covers 35 administrative districts. So the length is about 1,300 kilometers, and it's also regarded as lifeline of Madhya Pradesh and Gujarat because of its large contribution to the agriculture of these 2 states. And the majority of the population is directly dependent on agriculture. The rainfall significantly varies across the space and time. You can see that the rainfall is varying around 700 to 1400 mm across different parts. There is general gradient of also rainfall pattern. So these are the different data sets that we have used. Say rainfall from India Meteorological Department at the 0.25 degree resolution, and then groundwater level data has been collected from India Water Resource Information Systems provided by Central Water Commission. The population density we have collected from SEDAC database. Similarly, soil is from National Bureau of Soil Survey and Land Use Planning. So it's a 1:50,000 scale. And the elevation is, we have taken SRTM model to derive the distance from the river reach and elevation and slope. And then LULC map, we have taken the classified map of Copernicus Global Services, 100-meter resolution. So the overall framework, first of all, we have to collect the data and the preparation of various geospatial layers. First of all, we will rainfall-based dry air frequency, then depth to groundwater level, all population density, distance from river reach, and all these 8 layers we have prepared. Then assigned weights to each layer based on their how vulnerable, based on the subclasses, how vulnerable they are to droughts, and then overlaid all the geospatial layers. Then sum of weights from all the layers were decided what will be the comprehensive drought vulnerability indicator. So based on this, we divided into 5 different classes: extreme vulnerability to low vulnerability to droughts. So for these are the apart from the rainfall-based dry air frequency, other data sets were directly obtained. But the rainfall-based dry air frequency was computed using the standardized precipitation index. So this is the procedure for SPI, where the rainfall time series is fitted to suitable distribution, preferably 2 parameter gamma, and then we pointer is not working. Okay, so then its inverse transformation, that is inverse normalization, is carried out to convert it into a reduced variate of 0 mean and unit variance. So that will be the standardized precipitation index. So it is useful because it is very simple to calculate, and it represents both the dry and wet conditions uniformly. So we have taken the frequency of dry years as a factor for computing the drought vulnerability. So these are the weightage provided to each factor. So for frequency of dry years, since we have 120 years of data, there is, based on the equiprobability transformation, basically around 59 to 60 should be the average drought condition. So if it is less than 57, we have considered it lower weights, and if it is exceeding 62, we are considered the highest weight. So similarly, depth to groundwater level in meters below ground level. So if water is available much in the much depth, so it's more vulnerable to droughts. So similarly, in population density and distance from river reach and slope also, we have the higher the slopes, the more vulnerable to drought, because it will have a lower moisture retention capability. And similarly, for elevation also, we have given the weightage there, because the higher elevation zones will typically will have only the first and second order streams, because and they will have also have very low moisture retention capabilities. So that is why they are very highly vulnerable. On the other hand, in the lower slopes, which will be in the downstream side, they will be relatively flatter, and there will be higher order streams, so more water will be available, so which will make them very less vulnerable to droughts. Similarly, for soil also, the clayey soil will have a very high soil moisture capability, retention capabilities, because of their texture and size, whereas the rock outcrops and loamy skeletal soils will be more vulnerable to droughts. So similarly, for land use land cover changes, the agricultural lands will be highly vulnerable to droughts. So based on that, we have provided the weightage, and then the weights from all the layers summed up divided by the maximum possible weight gives you the comprehensive drought vulnerability indicator. So this is a very simplistic procedure to in a geospatial approach to compute the comprehensive drought vulnerability. So regarding the meteorological variability, we can see that the rainfall over the entire basin, the average rainfall over the entire basin ranges from 681 mm to 1600 time, okay, 87 mm. So the low rainfall years are getting more frequent in the second epoch, so which is showing a clearly declining, which is also evident from the clearly declining trends of rainfall. So these are the different types of drought, that is the frequency of drought in mild, moderate, severe and extreme category. So these are the different geospatial layers that we have obtained. You can see that the majority of the region is covered with agricultural land, making them more vulnerable to drought from the point of view of LULC, whereas in case of soil, most of the region is covered with the clay soil, clay and loamy soil. So this is also the population density, elevation and distance from the river reach. We can say that from the main stream of the river, so there is a majority of the region is having a high vulnerability. So we have overlaid all these 8 layers and found out this comprehensive drought vulnerability indicator. So based on the CDVI, we have divided into 5 different classes, that is non-vulnerable, less vulnerable, moderately vulnerable, highly vulnerable and extremely vulnerable. You can see that only around 5% of the area falls in the first 2 classes. So we can say that the most of the basin area is actually highly vulnerable to droughts. So this is again the reclassified map of the 5 different categories. So also, since we have the region covers 35 administrative districts, we actually tried to assess that what will be the vulnerability of these individual districts, and we found that 9 districts are falling under the moderately vulnerable, and 22 districts are falling under highly vulnerable, where 4 districts like Anuppur, Bhopal, Dhule and Indore are under the extremely vulnerable conditions. So no district has actually been in this lower non-vulnerable category. So the conclusions regarding the individual factors, LULC and distance from river reach of the basin were highly vulnerable conditions. On the other hand, soil and slope were less vulnerable in most of the regions. The overall CDVI revealed that a majority, around 66.4%, to be highly to extremely vulnerable conditions, and the district-wise assessment revealed no constituent district of basin is under non-vulnerable or less vulnerable condition, whereas the 9, 22 and 4 districts exhibit moderate, high and extreme vulnerability to droughts respectively. And obviously this study has certain limitations also, like we have not provided any weightage to individual layers, compared to other layers. And also we will be improving this study by computing SPEI in place of SPI in future. Thank you, and the financial support provided by the WCC is wholeheartedly acknowledged.
So, thank you very much for the presentation, and I think you have given us some quite alarming results that in the river basin that you looked at, for all the districts, even in the best case, you found a moderate level of vulnerability and sometimes even a high or extremely high risk related to droughts. We now have 2 minutes for questions on the presentation.
Thank you. We are bothered about vulnerability. No, actually, I understand your question. You are talking about the DRR framework prepared by the Sendai framework. So vulnerability essentially means the inability of a system to withstand a failure condition. So what we are looking after is like what are the, yes. Yes. No, we did not get the data. That is a major limitation, I understand. Thank you. That's a very nice suggestion. But the Narmada Basin, typically we do not get the data for this reservoir storage. We have tried to delineate this canal systems, which we will be incorporating in the future. Yes. Okay. Okay. Thank you.
We have 2 more hands raised. These 2 short questions, and then we need to continue with the next.
Yes. Thank you again. For very fascinating presentations. I will keep my question very short. So the topic of the talk is assessing the impacts of climatic and socio-economic changes on drought vulnerability. But by the end of the presentation, everything is put in a one single indicator as CDI, as I understand that is comprehensive. So just my curiosity that have you thought about decoupling to tell us which is more important? Is it anthropogenic or is it natural? So I hope my question is short. Thank you.
That's a very interesting question, first of all. If we see like land use, land cover changes, or we say this population density, we have considered as socio-economic factors. So if you can segregate them, you have 8 different layers after all. This is a very simple approach of overlaying all of them and adding on the weights. So if you can segregate them, you can always decouple them in that way. But it will be practically, it will be very difficult to convince as a scientist that what will be the more severe on a particular region, say, because the impacts are actually multifaceted. So we can always say from the climatic point of view by using the SSP scenarios what will be the changes in terms of frequency or duration or severity, but it will be very difficult to exactly predict in the same way for anthropogenic factors. That is another challenge. So that's a very interesting question. Thank you.
Hello. I'm directly going to my questions due to a restriction of time. Basically, I saw your presentation and you give us some layer map or to take some factors which you have to weight all these parameters. So which methods, or there are various methods, which matters more rely for this such type of generating the weightage of each layer? You don't describe about this.
This is actually, this was a user defined approach that we took, like based on this rationale that which subclass will be more vulnerable to drought. For example, in land use land cover, we said that agriculture will be have a maximum vulnerable to droughts. So in that way, we actually define. But after that, that's what I said, the limitation which I talked in the last, that we should provide weightage to individual layers compared to others, which can be done by this various MCD approaches, say analytical hierarchy process or TOPSIS. Those methods can be applied. So that will be a future course of this work. And right now, we overlaid all the layers and provided weightage to individual layers, I mean, to the subclasses.
Thank you very much. We will unfortunately not have time for another question now, but maybe we can come back to that in the discussion round after the 5 presentations. Let's give a last hand to Mr. Sabyasachi Swine.
Thank you.
And with that, I'm happy to introduce to you our next speaker, who is Mrs. Özge Naspala from Bogazici University, Istanbul in Turkey, who is also working on the city that she currently resides in, with a presentation on the assessment of flood vulnerability for urban decision-making, an index for the Istanbul metropolitan area. The floor is yours.
Thank you. Good morning. Good morning, everyone, and thank you for having me. My name is Özge Naspala, and I'm a master's student at Boğaziçi University Institute of Environmental Sciences. And today I'll be talking about our study titled Assessment of Flood Vulnerability for Urban Decision Making, an index for Istanbul metropolitan area that we conducted with Dr. İrem Daloğlu Çetinkaya. I pressed this one, but sorry. Okay. We have organized this presentation in the following way. First, I'd like to give you an overview of the relationship between cities and climate change, and we will move on to our research question and motivation. Thirdly, we will look at the materials we used and the method that we proposed. And finally, I will end with our findings and expected outcomes of our study. It will take about 10 minutes to cover all of these issues, I hope. As we all know, climate change and cities are strongly and deeply connected. More than half of the world's population is in cities, and urban areas are home to much of the world's industry. As a result, statistics show that cities are one of the biggest drivers of planet warming emissions. Because of the high population and building density, weather changes due to climate change are likely to greatly affect cities. Urban flooding is a critical challenge brought on by climate change for today's cities. In 2021 alone, about 4,000 people lost their lives due to floods. Similarly, floods are the second most destructive type of natural disaster in Turkey after earthquakes. Numbers indicate that the number of flood events after the 50s is more than 6,000 in Turkey. So let me first give you a brief overview of the background of our study. Our first concern was to find the criteria affecting flood vulnerability and to prepare an index for Istanbul with a multi-criteria approach. From this point of view, we set out by asking which criteria are more effective in flood vulnerability and whether we can identify certain vulnerable areas. Istanbul's vulnerability to urban flooding was analyzed using an index-based framework, and we basically completed the index creation process in 4 steps. First of all, we determined the common parameters by reviewing relevant literature, And secondly, we explored the available data sources. In the third step, the most suitable ones were shortlisted in the context of Istanbul. And finally, we created an index that brought together economic, ecological, and social parameters. The index we created consists of 9 different parameters that you see on the slide. These criteria consider different drivers ranging from the physical condition of buildings to the social structure of the population. Let's now take a look at our area of study. Istanbul, the largest city of Turkey with around 16 million inhabitants, suffered most from the flash floods. Factors such as land use changes, urbanization, poor drainage, and settling in the flood-prone areas worsened the consequences of the floods. Our study area, Kaynarca Stream Basin, is located in Pendik district of Istanbul, and the total area of the basin is around 365 hectares, and the population is approximately 185,000 people. As you can see from the satellite image, the basin area has low vegetation cover, low pervious areas, and high paved surface area. To assess vulnerabilities, we obtained 9 different data sets from official institutions. The demographic data for this study comes from Turkish Statistical Institute's last census. The building data is obtained from Istanbul Metropolitan Municipality. And finally, Istanbul Water and Sewer Administration's maps are used to evaluate flood risk. After the data collection process, we performed geospatial assessments and produced the input layers of vulnerability factors using geographic information system tools. Here you can see the illustrated version of our method. We started by dividing the area into grids of 2,500 square meters. Then we added the flood risk and social and physical vulnerability layers to the map. After that, we calculated the vulnerability score for each grid and produced an overall flood vulnerability map. So were these 9 criteria the same degree of impact on flood vulnerability? To understand this, we adopted the analytical hierarchical process method offered by Sati and applied a survey of 35 questions to 8 experts from 5 different backgrounds and asked them to score the criteria with the pairwise comparison methods. We actually achieved a satisfactory consistency with a ratio of 3.5, which was below the 10% limit set by Sati. This chart you see illustrates the weights of the criteria according to the respondents. The more important criterion had the greater weight in the overall evaluation. As the chart indicates, proximity to health services was rated as the least significant criterion, while proximity to the floodplain was ranked as the most important factor. I'd like to highlight that physical environments influence the vulnerability to floods more than economic and social factors according to our respondents. To calculate grid-based vulnerability score, the weights and standardized measures are combined using the formula you see. Finally, we calculated vulnerability score of each grid and divided it into 5 different classes from extremely vulnerable to very low vulnerable. And we obtained the overall flood vulnerability map of the area. We found that the high vulnerability is closely associated with the low quality of buildings, high population and building density, and the community's capacity to cope with disasters, namely low literacy rate, poor socioeconomic conditions, and the ratio of elderly people. As can be observed in the chart, 22% of the total area of the basin has low urban flood vulnerability. The extremely vulnerable and vulnerable zones together constitute approximately 40% of the total area. When we look at the vulnerable and extremely vulnerable areas closely, thank you. When we look at the vulnerable and extremely vulnerable areas, schools, student dorms, banks, markets, health centers, and other commercial institutions are located with high crowding compared to other parts of the basin. So it can be said that if any flood occurs, that will seriously affect the common public compared with the other locations. All in all, we developed a flood vulnerability index, adopting an indicator-based approach. Mapping the issue showed that vulnerability to flooding is not evenly distributed throughout our study of the study area. To conclude, vulnerability map generated in the study will help to identify the vulnerable areas of the basin and can be used to allocate resources properly to improve flood preparedness. Moreover, this study can be taken as a primary baseline data for prioritization of adaptation strategies. Finally, since the model allows user interaction, local authorities and planners can repeat their assessments periodically with up-to-date data. And that brings us to the end. I'd like to thank you for your time and attention today. If anyone has any questions, please feel free to ask, and I'll do my best to answer. Thank you very much.
So thank you very much for your presentation, and thank you also for keeping perfectly in time. So we do have time for 1 or 2 questions.
Okay, thanks for your kindly presentation. It is interesting actually. But if you are, from my point of view, just advice, I know you are a master students, so my advice for you, as our colleague from India, the first speaker, when he displays the vulnerability, he mentions the weight for each parameter.
Mm-hmm.
So
Yeah.
I expect that you display the weight because you displayed several parameters here as a technical session.
Mm-hmm. Yeah.
From your point of view, if
Yeah,
we
yeah.
speak about vulnerability, we need to know the weight of each parameter here.
Yeah,
You
yeah.
can say-
Thank you for
you
your contribution. Actually, I mentioned them in my paper, and to cover all of these issues, I tried to cut some part of the paper. Actually, charts indicates the weights, but yeah, thank you. I will consider it.
Okay.
Thank you. My question is actually it's a follow-up question about the weightage that was assigned. I think you mentioned respondents, but I missed that part. Who were the respondents and how were those weights assigned? And my follow-up question is if I observed that it was applied in Istanbul, and I was wondering if it can be applied elsewhere in another mega city, for example.
Yeah.
Thank you.
Okay. Our respondents were from local governments and academia and private sector actually, and they were environmental scientists, urban planners, and so on. And we sent them a questionnaire using pairwise comparison method. Which one is important for you? The proximity. We hope that it can be applied anywhere in the world, in megacities, but maybe the criterion numbers can be increased, or maybe the number of respondents can be increased. But we try to not to include the local characteristics of Istanbul, for example, migration situations or something like that. That is why we can apply anywhere else in Istanbul. But I don't know all the megacities, and we are now trying to apply it into different river basins in Istanbul. Maybe we can talk to you later about the results.
Thank you very much. Thank you.
Thank you.
Actually, this is also related to the questions of the first and the second, which is this is the very critical for the EHP because I am working with the same. How did you arrive with the SAAT scale ratio for each factor, for the combination of each factor?
I didn't understand clearly. How do I what?
How did you decide the SATI scale, the SATI scale.
Yeah,
Like-
yeah, yeah. Actually, we reviewed relevant literature and find that the AHP methods is one of the oldest and most trusted decision making methods, and moreover, it was easy to use for us, and this method allows you to check the consistency ratio of respondents. That was an advantage too. And finally, and most importantly, when we contact our respondents, many of them were familiar with this method and had previously participated in AHP questionnaire. That's why we chose this. But yeah, there are other methods and can be applied to all, but we chose that one.
So, thank you very much, Özge, also for
Thank you.
answering all the questions. Let's give a last applause to her.
Thank you very much.
And we will now continue with the next presentation. Our speaker is Mrs. Tisha Lolupinan, who is from the Hydroinformatics Institute here in Bangkok. And her presentation will be on drought indices, land use irrigation area nexus to develop a drought vulnerability index for drought assessment in Thailand. The floor is yours.
Yeah, thank you very much. Good morning, everyone. My name is Tisha Lolupinan, and this cannot. Okay, I'm a model developer from Hydroinformatics Institute, Thailand, and today I would like to present you about the drought index land use irrigation area nexus to develop a drought vulnerability index for drought assessment in Thailand. And so this is the content of this presentation. I will start for the introduction, study area and that data that we use, the methodology, result and discussion, and the conclusion at the final. So this is the introduction and objective. Drought is a phenomenon that's having a below normal precipitation over an extended period of time and ranging from the month to years. And actually there are 4 types of drought that are the first presenter present, including the meteorological drought, hydrological, agricultural, and socio-economic droughts. So in this study, we focus only on the agricultural and meteorological drought. And the main objective of the study is to develop a drought vulnerability index using combine the satellite data with the physical data. And the physical data that we use is the land use and irrigation area. And this is the study area and data that we use in this study. And study area is the entire of Thailand. And the data that we use, actually we use 2 main data. First is a satellite index, and the second is the physical data or the bed map. And the satellite index that we use is is the NDVI and RST from the MODIS satellite. And we also calculate it into the NVSWI or normalized vegetation supply water index. And we also use the SWI or soil water index from METOP satellite. This is the physical data. Physical data that we use a land use and irrigation area. Land use we derive from the land department, land developing department, and irrigation area we derive from the Royal Irrigation Department in Thailand. The reason that we use these 2 data because the impact of drought for each land use or the irrigation area and rainfed area is different, right? Irrigation area will be higher impact to drought. Drought will be occur in the irrigation area higher than in the urban areas. In the similar to the irrigated and rainfed. And this is the meteorology that we use. There are 4 main steps of the meteorology. The first step is the first is to calculate the NVSWI from NDVI and LST. And after we calculate NVSWI, we will got 4 index that we use. First is NVSWI, SWI, land use, and irrigation area. After that, we classify these 4 index into 5 classes and do the index weighting for each index. And we calculate the DVI as the result. And this is a metric that's how to classify. We use the value of each index. The lowest values means high impact, and the highest values mean low impact. And this is the weighting, index weighting. We didn't use the expert to define the index for each criteria, but we use the entropy weight method to do this one. Because sometimes we cannot, the expert don't have a time to do this, or we cannot find the expert. So, and this method is to avoid the uncertainty of the data. This method can solve the data that have high uncertainty, and the satellite data have high uncertainty. So this method is the best way to do the weighting. After we got the classification the different class of the index, after we got the weighting of each index, we do the DVI by using this equation that you see. This is an example of the comparing SWI and NVSWI, and based on the dates of LST in 2022, and the same interval is every 8 days. And the significant change in this drought index has a direct impact on the land use and irrigation. So that's why we decide to add the land use and the irrigation in for develop the DVI. And land use and irrigation is a physical data. It's not changed too much. So we decide to fit it into the base map and combine with the drought index. This is a DVI result and 4 different index. First is the NVSWI, second is the SWI, irrigation and land use. And we, after we combine it, we get the DVI result in the map. And you see in the center part of Thailand is a low value of the DVI, and because in the central part of Thailand is located in the irrigation area. So they have the water to use. But in the upper part of Thailand, in the high value of DVI, is located in the agricultural area and rainfed area. So we got the high value of the vulnerability. And we also compare this result with the record from the DPM. The DPM is the disaster department in Thailand. When we compare it together, it looks like similar. The result is similar to the announcement of the DPMs. So You see in the center part, the result from DVI is a low value, right? But the DPM is not announced for the drought situation in the center part, like this. This is a conclusion, and this study is developed the DVI for the entire of Thailand by understanding the nexus between drought index, land use, and irrigation area. The step to develop the DVI, we developed the NDVI map. NDVI is used for measure and analyze the plant health and drought condition in the agricultural area. And VSWI and NVSWI is can let you know the magnitude of the drought severity. And the soil water index is you can indicate the is an indicator of the soil water index, and it's important to the meteorological drought and agricultural drought also. And this study is under developing now. So next, in the future work, we will add more the index, such as the precipitation index or the rainfall or the runoff index, something like this, into this study, and we will do the operating system. That's why we use the satellite data to do in the study. So this is done for me. Thank you very much.
So thank you very much for your presentation, and once again we have time for approximately 2 questions. Not much more, unfortunately, as I have been informed that we must be super punctual in vacating this room after the session, as the Thai Minister of Natural Resources and Environment will be coming here and the room needs to be prepared. But let's now start with the questions.
Yes, thank you very much. My name is Angel Cruz. I am from the Philippines. My question is particularly because this is about decision making, how it connects to decision making by officials. Knowing this drought vulnerability index, knowing drought prone areas, what are the concrete, how does this link concretely with decision making on water resource allocation? Could you give an example?
Actually, we after we do this one, and after this project is finished, we will send the data to the local the government, and in the disaster government or some organization that relate to the drought, and to prepare or manage the drought situation in Thailand.
Last question.
Hi, again, thank you for your very insightful presentations. I enjoyed it a lot. Very quick question. Can you explain mathematically how you calculate the waste? I saw that you use one entropy method to calculate the waste. So can you explain the mathematics behind it? Thank you.
Okay. This is the last slide. So okay. Actually, there are 3 steps of the entropy weight method. The first is to do the standardize of the data. Second, calculate the entropy. This is the method to clean the uncertainty of the data. And the last one, we calculate the weighting for each index. Just, suppose that you have 4 index. The last one is weighting calculate is combine the 4 index together and calculate each weight.
Thank you for your explanation. Just to clarify, so the data with less uncertainty will have higher weightage, or what's the calculation?
This if the data have high uncertainty, right? Is we have the step to clean the uncertainty of the data, like have to cut off the outlier of the data, something like this.
Yeah, that I understand, but how from there you convert into the weight for that component?
Okay. Is it at the laser or no? Okay. So for the last equation you see. Actually, I did. Okay. For the last equation, is we have the component of the data for each component. It will be calculated in the last step, but the equation is not like show you the how to calculate the component of this one.
Okay, thank you, and I think more questions can later be dealt with, and I think this was a very important question, because when we define drought vulnerability, we have already had a first presentation that used a different method to, in the end, define what is a moderately or strongly vulnerable area in the sense of drought risks, and we will see in different presentations that different approaches are being taken to assess this, and this of course to some degree makes sense as we are speaking about different parts of the world, but we also see that this leads to a very different understanding of what in the end is drought vulnerability. But let's give a last applause to Tisha. Thank you for the presentation and answering the questions. And with that, I would now like to introduce our next speaker, Juliane Huth, who comes from the German Remote Sensing Center and who will be looking at the observation of climate extremes, looking at a project in Vietnam that looked at drought and flood adaptation.
Hello to everyone in the room. Oh, I have to adapt this to my larger size. I want to present on the two extremes, drought and flood, and the adaptation to that. The presentation is on behalf of many people, as you see, so it's two big research projects. So my name you see, and the other one who's also with us in the room is the project leader from the Drought Adaptation project on the German side, on the Vietnamese side, Dr. Nguyen Nia Hung. You can also ask him questions later on that. So I want to start with the introduction of the situation in the project regions in Vietnam. Floods and droughts frequently occur in this country, so it's not unnormal. But what is unnormal is that droughts are more frequently reported in the last years, and that floods induced by typhoons and other storms are frequently occurring, but they are expected to increase in number and strength. So governmental and non-governmental institutions call for evidence-based information to research on that and the development of adaptation concepts. Therefore, we introduced two independent German-Vietnamese research projects that started in 2019 and 21, which aim at bilateral research cooperation to contribute the results to the regions. I want to start with the first one. It's called Drought Adapt. It's called Adaptation to Drought and El Niño Effects in the Central Highlands of Vietnam. What does the project want? So the project wants to develop innovative approaches to support medium, short-term and long-term planning and adaptation measures to drought situations in the Central Highlands of Vietnam. the project is working at different scales. On the one hand side, there is engineering solutions, technically innovative to the local level, and there's a second scale working on a provincial level where we want to come up with innovative climate services to encourage provincial authorities to adapt to the impacts of climate change. This is the project concept, just very briefly. It is combining Earth observation, dynamic modeling, and adaptation concepts to transfer this in one result that we use the climate service approach for, and knowledge transfer to the region. I want to highlight every single thing just in one slide, so very briefly. I want to start with the Earth observation. This is the field where I'm coming from, so I'm leading this project, but my second head in this project is also doing the remote sensing work together with other colleagues of mine. So this is what we started with just recently. Preliminary results is the analysis of drought for mainland Southeast Asia to find out which years, like data-based, evidence-based, which are the drought-prone years. It's the analysis of vegetation cover with the vegetation condition index for the years 2015 to 21. And you can see on the red arrows here which years, so 21, 20, 19, 16 are years that already from the vegetation cover status in mainland Southeast Asia are drought prone. What we also need to do for the area to enhance data sets, land use is available from many sources globally, but we want to come up with a higher resolution data set and use time series approach and classify the sentinel data with cloud processing environment to come up with a multi-class line cover. Now I'm coming already to the work of my colleagues. So the dynamic modeling starts with one topic, the hydrological modeling, where the colleagues worked on, as I said before, so different scale than we do in other part of the project. So they are working on the 2S basin, so part of the Mekong inflows. And they are using the open source model MHM2S and got some first nice results. What they also do later do is drought forecasting. So this is just the first step that they did, which works quite reasonably. Even a larger scale on the mainland Southeast Asia, people working on climate modeling. What is also important, data input to our results. And another project group is bringing already quite some of those data together, and they work with water availability on the crops in their area. So they are working on water crop demand and researching on adapted irrigation technologies. What is also important to come up with is some measurement equipment installed in the region. So this is also some kind of concept for this approach that we also get the data from the site. Also talked about with stakeholders and get suggestions for the locations there. What is always very important is to analyze also the policy framework. So we have a group in our team working with recommendation for actions. They work on the analysis of ecosystem-based adaptation approaches available in the area, but also on workshops and interviews which could be applicable for the area. And they work on literature review for national framework conditions, and at the end of the project want to come up with recommendation for actions for change and adaptation to the climate. The main goal of the project, as I said before, is the prototypical implementation of a climate service. So what is a climate service? It's a concept known by the WMO, and we came up with an adapted definition that you can see here. So a climate service is a customized and demonstrable prototype to help authorities to make climate-informed decisions for adapting to drought impacts, in our case for the regional level, and in the context of climate change. And what I want to highlight here is the last row. So it's the combination of research results and the integration of the research results that I presented before to a prototype of a climate service that needs to be tested by local authorities, also again in workshops and discussions, and transferred there to potentially get reactions and informed decisions. So that's the first project. And now I'm coming to the next project that we are leading. It's it's mainly by accident that the project names are quite nicely comparable. And they are working on flood risk in the Central Highlands of Vietnam. So this flood adapt project is wanting to reduce current and future flood risks in the central of Vietnam. And they want to understand and assess the drivers and spatial patterns and dynamics of present-day floods and future flood risks in the area. They want to come up with disaster risk reduction information and implement this also to the local stakeholders that they're working with. And there's a co-development of a decision support tool for risk-informed planning. So where is this area located? It's different to the other one. So it's here in the center of Vietnam. It's the Hue province. You can see a satellite image of there. And why are they working there? So there was the project started in 2019, but it is already showing during the last years that it's important to have such a project. There was a pronounced flood in 2020, where in Hue province there was large floods and also loss of lives and big damage. It was induced by 1 or 2 typhoons, I guess. And comparable, half year later, there was also pronounced flood in Germany. Maybe you heard about it, where also was a lot of life loss and damage to the local population. So how do we deal with the data in this project? So this is the flood-prone area in 2020, but I just showed a picture 1 minute ago. And we're analyzing satellite data. What is also important to know is the shoreline detection of this area, but over a longer period of time. So this is data set from 1987 to 2020, where satellite data analyzed to find out about the change of coast in that area, because this is, so typhoons So then the people came up with the analysis of the current flood risk and impacts. They want to assess the current floods to combine this for later information on the future floods. So this is analysis of modeling for the flash floods and river floods, and the first results on the right-hand side. What is important for that is also to, into flood risk scenarios, also integrate urban growth scenarios and SSP social pathways, socioeconomic pathways scenario, where we also used satellite data for. Important is that several qualitative and quantitative measures are used to come up also with in discussion rounds, in criteria analysis, and adaptation measure models and concepts to find out which adaptation options are most appropriate for Hue. So I skip this now. And at the end, the digital infrastructure behind that in the Flood Data project is the Flood Risk Adaptation Measure and Evaluation Framework, which collects, stores, and visualizes all spatial data and the statistical data, and integrates the new planning approaches. So I now want to have a last slide to show you how we combine all this. So we work very closely together in our group and with the researchers on drought assessment and on flood assessment, and we think that research cooperation together with the exchange with the local stakeholders is most important to come up with adaptation concepts in this region, but also in very many other regions of the world. So we thank our ministry for funding this in 2 different funding bodies. Thank you so much.
So thank you very much for introducing to us studies from Vietnam, which showed that in actually the same region of the country you need to look at flood and drought risk adaptation. We have time for 2 short questions. Firas?
Thank you very much for your presentation. Firas Al-Janabi from the ABCD Center. Now from your presentation regarding the flood adapt, you are focusing on the post-flood, not pre-flood events, and the data is only images. Is that correct? Or there are some other data, satellite data, that you are using for the flood? So this is the first part. The second part is I'm also interested in this tool for decision making that we are planning. Can you tell us a little bit about it? Thank you.
Thank you for the questions. I have to admit that I'm not the project involved in this project because I lead the other project, but I can answer your questions a bit. So the data for flood assessment, of course, is time series data for from satellite, but also for the model data, there's also measurement data available from the region. So the model are so the hydrological model, of course, are modeling the past, the current, and the future, and validated with satellite data as well. So with the extents taken from the satellite. And with respect to the decision support tool, I have to admit that we maybe exchange contacts, and I'll let you know later, because this is undergoing work in the other project.
Thank you. Last question to Professor Ribbe. Your microphone is turned off, I think.
Yeah. Excellent presentation. Thank you very much. Good example how to combine measurement, modeling, and also policy issues. We had a similar 5-year funded project, BMBF, some time ago in Vietnam, and I think not only us, most of the projects I observe, they struggle then how to implement the results, but even, or simpler, how to keep the knowledge, you know, and really make it beneficial in the future. I have not really come across a project where that really worked well, you know. So what are your plans for that? It would be really interesting. And also, well, you said research cooperation. I think then, yeah, how can we all perhaps also join forces in order to make that knowledge that you create and so many others is transferred into the future and is made available to the decision makers. I think this is one of the big questions we have to somehow solve, no? So it would be interesting to see how you're addressing it, and you mentioned your Vietnamese partners are here. Perhaps there's even a chance to exchange a bit on that, no? Because I just come from Hanoi. I was there yesterday and we had similar discussions, no? Which is always, I think, not only in Hanoi, not only in Vietnam, anywhere in the world, I think the one of the key questions, no? To bring knowledge into action at the end.
Thank you, Professor Ribbe, for this question. Very interesting and very important question, of course. So as we are in the first research phase, this is what we are doing at the moment, right? Research. And the most important thing is to already now contact very closely the stakeholders who are interested in that topic and who are responsible for implementing this. So we, of course, as all research project, want to have a second phase for implementation. And yeah, most important thing is to keep closely contact with the stakeholders that are working there. And then what we in the research phase can do is publish, and get people from the country in our project as PhD candidates, who will go back to the country to implement things. So our project leader is the best example. So he was in the very former project Wisdom, which you know, candidate in this project, and very successfully went back to Vietnam and got a nice high position there, is now leading the project on the other side. So I think implementation and knowledge exchange is a lot based on science, research and cooperation. And we can discuss further, and I think he has also a comment. That's nice.
One short comment.
Yeah, thanks for the concerning. My name is Hong from Southern Institute of Water Resource Research, and I think it's a PI of the drought adapt projects, and I think that is for knowledge dissemination and the knowledge transferring is very important for implementing project. So Baijulan already mentioned about approaching long-term, short-terms. But we also have a master planning for the country. So this moment we are developing the master country for like very inter and multidisciplinary master plan. So I think those results when we come into the master plan and recommendation directly to the central director board or decision maker. But we also have approaching with a provincial and local level for like working with them and detail upgrading the system and stakeholder in lower level of this project. So thank you.
Thank you very much for adding this comment, and I would like to thank you to actually both Juliane Huth and Mr. Hung, who was mentioned as the co-author of this presentation, and I think it's the perfect example that science in the end can really best serve a purpose if in the end governmental master plans actually consider the outcomes of the scientific research. Let's give a last hand to both of them. We now quickly need to proceed with our program, as I was informed that we need to finish the session absolutely on time, and I would therefore like to invite our last speaker, Mrs. Hermanti Sharma, who is originally from India, currently working at the University of Tübingen in Germany, but presenting about a very different region, namely the coastal cordillera of Chile in South America, asking the question of the impacts of extreme precipitation events on catchment erosion. The floor is yours.
Hello everyone. So in this talk, I will emphasize on the sensitivity of distinct climate and ecological conditions on catchment erosion during extreme precipitation events in the Chilean coastal cordillera. This is the outline of my presentation. I'll start with the motivation and with the interpretation and conclusions. So, tectonics, climate, and land cover together influence the landscape evolution. However, extreme precipitation events play an essential role in shaping the landscapes. During extreme events, we see insignificant tectonic effects, and land use, land cover, and precipitation, mostly magnitude and intensity, influence the catchment erosion. Now, in this study, land use, land cover refers to basically vegetation density and type, primarily as grasses, shrubs, trees, etc. Now, the aim of this study is to disentangle the impact of land use, land cover, and precipitation on catchment erosion during extreme precipitation events. Now, the hypothesis of this study is that if land cover distribution is the first order driver of erosion rates, then regions with less resilient vegetation cover, mostly grasses, would be more vulnerable to erosion during extreme precipitation events. This is despite the prevalence of high magnitude precipitation events in the regions with dense vegetation cover. To tackle this problem, we use a complex numerical landscape evolution model, LandLab, which is modified to account for the land cover distribution. Now, the study, we have 4 study areas in the Earth-Shape, in the regions funded by Earth-Shape program, which is a priority program of German Research Center. The environmental gradient varies from arid region in the north in Pandiazukar to semi-arid Mediterranean and humid temperate regions in Nawal Bhuta. This is the land cover distribution from north to south as A, B, C, D, ranging from barren land mostly in the north to mixed grasses and barren land and shrubland in La Campana, and a dense forest in the southern catchment. This is the time series of precipitation events. It's the stochastic distribution of precipitation on daily time scale, and the El Nino years are highlighted. However, the El Nino events are more prevalent in the northern 2 catchments, but we've highlighted for all the 4. Now, as these regions experience similar tectonic and lithological settings, we have assumed the rock uplift rates to be uniform in all the 4 catchments, and the lithology is an igneous rock, mainly granodiorites. Now this is the experimental setup. First I will talk about the landscape evolution model here, depicted as this topographical feature. So the initial topography we have from the DEM extracted from SRTM at the spatial resolution of 30 meters. And the main processes going on is constant uplift rate and precipitation at daily time steps, erosion, fluvial and hill slope processes, and these equations of erosion and sediment transport are modified based on the land cover distribution. And the major hydrological processes involve evapotranspiration and infiltration and surface runoff. So here I have also mentioned that where I took the data from. Now, due to the lack of observation data to validate the model, we had to rely on a simple physically based hydrological model SWOT to produce the runoff rates, and then we cross-checked the landscape, LEM and hydrological model outputs to validate the model. So we used the catchment outlet runoff rates, which were normalized by the catchment area because both utilize different geometry of the model. So here we plotted the runoff rates from both the models with each other, and we calculated Pearson correlation coefficient, which is denoted as R in the right figure. And we observed that we get a good correlation between these 2 models, more than 0.8, with a significance level of more than 95%, and hence we can say that the model results obtained from our landscape evolution model are validated best to our capacity. Now here I've plotted the precipitation rates with erosion rates, and the points marked as stars are the days with maximum precipitation. So to keep our life simple, we just we call these days as events, as extreme precipitation events. We also plotted the erosion rate change in all the study areas, which is calculated as defined in this figure. And we observed that we see a drastic change in the semi-arid region, which is Santa Grazia, and all the other 3 environmental settings experienced a similar change. Now, similar to previous figure, we now this is the extreme event, and on figure on the right, on the left, denotes the fraction of mean annual erosion during one precipitation event, which was star marked in the previous slide, and on the x-axis we have precipitation rates during that event, which is in millimeters per day. And we observed that in semi-arid region, that is Santa Grazia, almost 1/3 of annual erosion occurs during one event. However, in the rest of the 3 study areas, we observe around 7 to 12% of mean of the ratio of mean annual erosion during these extreme events. In the figure on right, we have plotted the spatial distribution of erosion rates with respect to mean annual erosion. So the blue color represents we get less erosion, and the red color represents ratio which is higher than the mean annual erosion. And here also in the spatial distribution, we can see that the semi-arid region, which is on the top right, is more sensitive to erosion during that extreme event. Now here, I would like to revisit my hypothesis that if land cover distribution is first order driver, then region with less resilient vegetation cover would experience more erosion. Now we had two regions, arid and semi-arid, in this category. However, we do not see a very drastic change in arid region. The reason being that we do not get very high magnitude precipitation events in that region, and however, due to El Nino events, especially in the semi-arid setting, which constitutes mostly of 29% grasses and little bit of shrubs, we experienced 1/3 of annual erosion, which is again significantly reduced in the regions with dense vegetation cover down south. And secondly, we observed that during precipitation events, the vegetation type, here we can also call it as land cover distribution, pose a first order control on catchment erosion, especially in the semi-arid settings. And the effects of precipitation variations are secondary. So a take-home message is that what we observed overall is that the semi-arid regions are very sensitive to the extreme precipitation events, and as we saw that land cover distribution plays a very important role in such an event, so we need to be more careful and plan better mitigation processes in these kind of regions. Thank you.
Thank you very much for your presentation. And I have been informed that we unfortunately need to leave this room now, as it has to be prepared for the minister's visit. I would therefore like to ask you for a few minutes to just come outside to maybe one of the coffee tables, so that if you have any questions to Hermanti or any of the other speakers, we would all be there for a few more minutes if you wish to discuss. And after a short meeting out there, please all proceed to lunch. Thank you for all the question and discussion that we had in this session.
Hello. Hello everyone. I have an announcement to make. So we'll have our lunch on Thanya Buri Hall. So our student volunteer will guide you to the Thanya Buri Hall. Thank you.